Yes, sir.
Okay, let's start. So, okay, to summarize, we studied the one variable case, how we can find the maxima, minima, how we can basically find the critical points and then decide whether the function is at its maxima or minima over there. And then we move to the case with two variables where we also found the critical point. We saw the two conditions. One of the two conditions holds. Okay. So a particular point is a critical point if, see, first you will check whether the derivative doesn't exist. Now, when does the derivative doesn't exist? For example, if the function is like mod of x, then the derivative will not exist at x equal to 0. So wherever the function is not continuous, uh, so not continuous, you can easily make out from the graph or from the definition. Not differentiable means uh, when there is a sharp turn uh, to the graph, like in case of mod function. Okay, or uh, if there is an asymptote there. Okay, so in case of tan, there is an asymptote at 90. So those functions are not differentiable. So either the derivative does not exist, or if it exists, then derivative of x is equal to derivative with respect to x is equal to derivative with respect to y, and both are equal to 0. Then it is a critical point. Okay, then we saw one method, and let me just summarize this method as, so basically, if the given function can be expressed in terms of sum of two square terms, that is z is equal to x square plus y square. Okay, then it is a paraboloid. It is basically this paraboloid, z is equal to x square plus y square, paraboloid which opens upwards. If it is z is equal to minus, so what happens in this case? It has absolute minimum. Okay, it has absolute minimum at x, at its vertex, that is x equal to 0, or in short I can say at 0 comma 0, which is its vertex. Okay, so the given function you can express as sum of two square terms, and you can uh, find out if it is of this form, then it is absolute minimum at x equal to 0 and y equal to 0. If it is the negative of the sum of two square terms, that is the coefficients of x square and y square, if they are negative, both the coefficients of x square and y square are negative, then it will also be a paraboloid. Right, this is paraboloid upwards, this is paraboloid downwards. Okay, downward, just the opposite of the first case. And it has an absolute maximum, it has an absolute maximum at its vertex, that is 0 comma 0. The third case is one of them is positive, one of them is negative, that is uh, it is either x square minus y square, or uh, y square minus x square. One of them has a negative coefficient, then it produces a saddle point. It produces a saddle point at its vertex, you can say 0 comma 0. So saddle point is just like inflection point. recall inflection point that we saw in the previous lecture in case of one variable. Okay, so you feel that the function is uh, going in one way till that point, and then suddenly the behavior flips at that point and becomes opposite. So we'll see the example of saddle point after a while, but it is just like the inflection point in 3 dimensions. Okay, the earlier one was in 2 dimensions, this is in 3 dimensions. And so basically it's a saddle point and you cannot decide in that case. It's a saddle point, you can say, but it is neither absolute maximum nor minimum. You cannot say that basically. So now coming to the second partial uh, or second derivative test. So in this case, we have second partial derivatives. Okay. So as you can see, there are because we have two variables. So one possibility is f of x. Now f of x means the first partial derivative was with respect to x, and the second partial derivative also is with respect to x. Second possible case is first partial derivative was with respect to x and second partial derivative is with respect to y. Third possibility is first partial derivative was with respect to y, second is with respect to x, and fourth final possibility is first as well as second partial derivative you take with respect to y. So these are the four possible second derivatives, second order derivatives in case of partial derivatives. Okay. So okay, now the thing is, so either you differentiate with respect to x first and then y, or you differentiate with respect to y first and then x. Okay, notation is different, you can say fxy and fyx is different, but their value will be the same, so they are equal. Okay, different operations. In the first case you are differentiating first with respect to x and then with respect to y. In the second case you differentiate first with respect to y, then with respect to x, but their result comes out to be the same. Okay, so effectively you have three types of derivatives to calculate: f of xx, f of xy, and f of yy. Okay, so now, so coming to the second, like we had second derivative test, we had second partials test. So in this case we define another quantity basically which involves all these partial derivatives, called as d. So d is equal to f of xx at the point xc comma yc. Okay, we'll go to the flow, but first we have already found the critical point xc yc, and then we are applying the second partial test, like second derivative test. So f of xx multiplied by f of yy at the point xc comma yc minus f of xy xc comma yc into f of yx into xc comma yc. Now because these are equal, so you can just keep one of them and d becomes f of xx xc comma yc into f of yy xc comma yc minus f of xy f of xy at xc comma yc the whole square. Okay, the square of this term. So okay, now after calculating this term, which looks like we can call it as a Okay, after calculating D, okay, these are the four checks. First is D greater than 0. If D is greater than 0, there are two possibilities. First is f of xx at xc comma yc is greater than 0, then it has a local minimum at xc comma yc. Okay. Second possibility is if f of xx is less than 0, then it is a local maximum at xc comma yc. Okay. If this quantity d is less than 0, then there is a saddle point at xc comma yc, and if d is equal to 0, then we have no conclusion that can be drawn. If d is 0, there is no conclusion. No conclusion means not even, we cannot even say whether it is local minimum, local maximum, or saddle point. In this case, then you will have to use some other methods. Maybe look at its graph, or maybe try the completing the squares method, something like that. Okay. Whereas, so these are conclusive. You don't need to test anything else. But in this case, at d equal to 0, you will have to do something else. You will have to test something else. Okay. So let's take an example. Okay, let's take a look at the saddle point first. Okay, so I'll share how saddle point looks. Okay, so yes, so this is an example of a saddle point. The same tests are given. The equation of this graph is actually x square minus y square, or the other way around, it is y square minus x square. It will just flip down. So if you see, it looks like a horse, uh, saddle on the back of a horse. That's why it is called as a saddle point. Saddle point is at the center, that is the vertex 0 comma 0. So if you take the cross section of this shape, or of this entity, of this function, okay, x square minus y square, uh, if you take the cross section with uh, y equal to 0 plane, okay, y equal to 0 plane means the plane, or the plane which passes through x and z axis. Okay, uh, passes through in the sense, like normally we have x and y axis on the plane, and z axis points outward or inward into the plane in normal cases. So in this case, the x and okay, so like this, it is the plane where value of y is 0, that is all along the uh, x axis and along the z axis basically. So when you take a cross section, or if you simply look like this, okay, so if you take a cross section in this way, okay, then you get an upward facing uh, paraboloid, or upward facing shape. So it will feel like a local minimum at the vertex. Whereas if you take a cross section here, okay, you will get a downward facing paraboloid kind of a shape. So it is like a local maximum in that case. Okay, so basically it's like just like an inflection point but in 3 dimensions. Okay, so let's let's look at an example. Okay, so the example is of xy is equal to 4x square plus 9y square plus 8x minus 36y plus 24. Okay, so first derivative 8x plus constant 8. First derivative with respect to y. As it is, you also solve simultaneously and you can verify whether you're getting the same things or not. So derivative with respect to y will be 18y from this minus 36. Okay. So now from these equations, you can see that derivative exists. So we'll have to equate both to 0. X is -1 and y is 2. Okay. Directly from these equations, critical point is -1 comma 2. Okay. Then finding second derivatives now. Okay. F of xx is equal to 8. Okay, f of xx at -1 comma 2, f of xx at -1 comma 2 is 8. F of yy at -1 comma 2 is 8, 18. Of xy is equal to f of yx, which is equal to 0. Okay, now calculating the determinant or d. Okay, so d is f of xx into f of yy minus f of xy square. Uh, Everywhere you have to write those, you have to write -1 comma 2 at the point -1 comma 2. So here 8 into 18 is 144 minus 0, which is 144. Okay, now d is greater than 0, therefore no saddle point. Okay. D is greater than 0 and f of xx at the critical point -1 comma 2 uh, is 8. Okay, so therefore it is local minimum at minus 1 comma 2. Therefore local minimum at minus 1 comma 2. And you can also calculate the value. You can substitute the value in the function. You substitute x is minus 1, so it will be, and y is 2, so it will be 4 plus 36, 40 minus 8, 32, minus 40 plus 24, minus 40 plus 24 is minus 16, so is equal to minus 16 is the minimum value. Actually not even local minimum, actually we know, okay, but because we are not creating a paraboloid here, so we cannot say it is absolute minimum or what, but in this case it is like an absolute minimum as well. Okay, but in any case, like in case of second derivative or in this test, we do not use the word absolute as such, we just say local. Okay, but it is absolute as well. And see, so any questions, any doubts up to this point? Yes, actually yes, minus 16 is the global or the absolute minimum. Okay, do you want one more example or this is sufficient? One more example? Okay. Okay, find the critical points. Verify whether you get the same. Okay, can I make a change? Okay, I'll just make a change. Okay, you have already solved it. Okay, I'll make a, I want to make a change to this problem. Not a, okay, so instead of square term, let's make it a cube here. Okay, okay, so now, and here we have minus 3 as well. So if you start with the second equation, so for critical point, for the critical point, gx 0. So starting from here, we'll get y is equal to 3 minus 2x by 2. Okay, and here we already have 2y. So the first equation will become x square plus 3 minus 2x minus 6 is equal to 0, or x square minus 2x minus 3 equal to 0. X square minus 3x plus x minus 3, that is x minus 3 into x minus x plus 1 is equal to 0. So now there are two possibilities: x is minus 1 or x is 3. Okay, and accordingly, when x is minus 1, y will be 3 plus 2 by 2, it is y will be 5 by 2, and when x is 3, it will be 3 minus 6 upon 2, which is minus 3 upon 2. Okay, so x will be minus 3 upon 2. Okay, let me see what you have written in chat. Minus 1 3. Yes, correct. So now calculate the second derivatives. Okay, which is like second partial derivatives, in short, second partials. So, so g of xx, g of xx in general is, yes, g of xx is 2x, g of yy is 2, and g of xy is g and not g. So g of xy is equal to 2 as well. So now d at the point minus 1 comma minus 1 comma 5 by 2, d will be g of xx multiplied by g of xx multiplied by g of yy minus g of xy square, which will be equal to minus 4 minus 4 minus 8. So this is a saddle point. Okay, so saddle point f has a saddle point at minus 1 comma 5 by 2. Now testing for 3 comma minus 3 by 2. So this is equal to 8. Okay, so now in this case d is greater than 0, so we'll have to consider further. G of xx at 3 comma minus 3 by 2 is, because g of xx is 2x, therefore it is 6, which is greater than 0. So it has a local minimum, or in fact now we cannot comment because this is not our regular paraboloid, so let's not get into that. So let's just say it is a local minimum, because it doesn't matter. Okay, so local minimum at 3 comma minus 3 by 2. If it is a known shape like a paraboloid or something, then we can, or known 2D function, then we can say whether it is local or it is absolute. But in this case it's fine. Okay, we can just say that it is a local minimum at 3 comma minus 3 by 2. It may also be the absolute one, but saying it is a local minimum is also sufficient at this point. And what is the local minimum value? So g of 3 comma minus 3 by 2, if you substitute, okay, tell me the value of the function here. Is it minus 29 by 4? This is the minimum value of the function. Just verify and let me know. Any replies on the chat, or I'm not able to see it? Any questions, any doubts you have? Do you get this working? Shall we proceed to the next topic? Yes? Okay. So gradient descent. So we have learned linear regression, different types of linear regressions in the previous semester, as well as you have as you are learning classification in data mining. In both cases, we have a predicted value at a certain point, and then there is an error, which is the actual minus the prediction. Okay, so y is equal to f of x, you can say, and in case of one variable, let's say let's start with single variable functions. So uh, in simple linear regression, we only had one variable. So y depended on only one variable x, and then we build that table and we try to minimize the error. Similarly, in case of classification, you always have certain measures to calculate the accuracy of each method and calculate the error basically. Okay, so our goal here is to minimize the error function. Okay, so the error function is also called as loss function. Loss function, nothing but the same as the error function basically. Okay, and we want to minimize this error function. Now generalizing to the case where there are multiple variables. Okay, so I'm introducing this terminology here, and I'll also explain why this terminology. So let's say uh, y is your variable of interest. Okay, y is your variable of interest, and there are multiple variables on which y depends. Okay, so y depends on x1, y depends on x2. Okay, and so on. There are, let's say, there are n variables on which y depends. So when I say y depends on them, so it means that the equation of uh, the you can say y is of the form y is equal to some coefficient multiplied by x1 plus some coefficient multiplied by x2 plus some coefficient multiplied by xn and plus some constant, or you can say m1 m2 mn plus b. Specifically, I'm using the alpha here, that is y is equal to, let's say, the coefficient of x1 is w1, coefficient of x2 is w2, and coefficient of xn is wn plus b. So here we can write this as x1 is not taken directly, it is weighted with a weight of w1, x2 is weighed with a weight of w2, and xn is weighed with a weight of wn, plus there is some constant b. Okay, some constant b. Okay, not immediately, but let's say in the next lecture or somewhere, I'll introduce the concept of neural network for a short while because we'll need it for certain things. In in the case of neural networks, these are exactly called as the weights. These are the inputs to your neural networks, and then there are layers which we'll see, and this is called as the bias. Okay, the constant term is called as the bias, and these are called as the weights. Okay, so the loss function is expressed as L of W. Now, where W is the vector of the weights, W1 up to Wn. Why? Because this is again a concept like you are basically varying the coefficients W1 up to Wn, and you are trying to find out which particular configuration of these weights will lead to the minimum loss. So we have to find the minima, or we have to minimize L of W, where W is W1, W2 to Wn. It's a vector, just like we have seen in multivariable functions before. We express all the variables as a vector, just like that it is here. And let's see, so how we proceed with gradient descent. Okay, so there is another name for this function. It is also called as a cost function, also called as the cost function. Okay, in general, because in this module, which is named as optimization, any function that you have to either maximize or minimize is called as the uh, objective function. In general, it is an objective function. Okay, and in this case we have to minimize because it's loss or error or cost. But if it is profit or output or some productive kind of a thing, then we'll have to maximize it. But here let's focus on gradient descent, which focuses on minimizing the loss or the error function. Okay, uh, so we already have seen the concept of a gradient, slope, derivative. Okay, so let's not get into that and directly go to uh, okay, now we are not applying calculus directly as such. First, look at this concept. Okay, calculus in the sense we are not applying the second derivative test or second partials test or anything like that. What we are doing is, so let's say the function f of x is x square. Okay, uh, it's a parabola. All of you know the shape of x square. So f dash x is 2x, and f dash of x is 0 when x is equal to 0. And here we need not even perform any test or anything, we just know that it is the absolute minimum because it's a very known function. This is the absolute minimum of this function. Okay, but let's say we don't know. Okay, we we use first derivative test, second derivative test, and it's a very roughly shaped function, like a randomly shaped function, which is which happens very often in case of machine learning, deep learning kind of algorithms. So let's say it is a certain random function, any kind of random function. Okay, and we are at this point, or and there are some other points. Let's say, let's focus here. Okay, so we are traveling along the graph somewhere, and let's say we are here right now. Okay, our algorithm is here. Okay, so okay, the basic principle of gradient descent is, if the derivative is positive, the function, first derivative is positive, the function is increasing. Don't move in that direction because you are moving away from a trough. Peak trough terminology was introduced yesterday. So we are moving away from a trough, So if the derivative is increasing, don't move in that direction, come back. If the derivative is negative, okay, if derivative is positive, function is increasing, don't move in that direction. If the derivative is negative, the function is decreasing, keep going in the same direction because you are getting closer to a trough. Okay, so let's say we are at this point. Okay, for simplicity, let's just take this subsection of the graph and let's say it behaves like uh, it behaves like x square. Only this particular portion of the graph, let's say it behaves like this. For simplicity of discussion, I'm saying nothing else. Okay, so this is, let's say it resembles this. So at this particular point, the derivative is also 2x. Okay, in this particular region, let's say. Okay, or you can also assume that, let's say we are dealing with f of x equal to x square, and we just want to find its minimum very mechanically, not looking at the graph or anything, just mechanically. Okay, so let's say we are at the point, and this point is, let's say, -1. Okay, we are at the point, this is the 0, this is -1, so we are at the point -1. At the point -1, derivative is -2. Okay, 2x, derivative is -2, derivative is negative, function is decreasing, so keep moving in the same direction means increase x, increase x. Okay, because the function is decreasing, increasing x will decrease the function further. Okay, so increase x, but by what size? Okay, so increase it by the size of the gradient, increase it by the size of the gradient, let's see. So the gradient in this case is the absolute value of this. Gradient is 2. Okay, the gradient is 2 and minus just indicates that it is decreasing, but the absolute value of the slope is 2. Okay, so what you will do is, x was -1, it becomes -1 plus 2, which is equal to 1. Now what will happen? F dash at 1, f dash at this new x is 2. It is increasing. Now, therefore, the function is increasing. Derivative is positive, therefore, the function is increasing. So, now move in the opposite direction. So, what we'll do? You will decrease x, and by what amount? By the size of the gradient. So, x will be 1. Size of the gradient is 2. Because we want to decrease, we will do -2, and x will become -1. Okay, so if we directly add or subtract the entire gradient, we are in a way, so uh, we were here, then we moved to this point, then again we decrease x, we again move to this point. Okay, so we have to have some adjusting factors, so that we don't want to add the entire gradient. Okay, we want to add certain fraction of the gradient. Okay, so let's say we decide something called as a learning rate, or in simple words, it is nothing but the step size, learning rate or the step size. Okay, so it is indicated by eta n with an extended line like this. So eta, let's say, is equal to 0.25. Okay, we use the step size 0.25. So now we'll multiply the gradient. We'll not add or subtract the gradient directly. We'll multiply the gradient by this step size, by this learning rate first. So initially we are at -1. Okay. Now we want to move in the same direction. -1 plus the gradient multiplied by the step size eta, which is equal to -1 plus 0.5, which is minus zero point 0.5. Okay. So f of f dash of 5 is -1. Still, the derivative is negative. The function is still decreasing. Keep moving in the same direction. X is -1, sorry, minus 0.5 minus 0.5 plus the gradient value is now 1. Okay, don't take -1 or -2. These are the values of the derivative. Value of the gradient here is the absolute value that we are considering. Magnitude, you can say it is 1, and step size is again 0.5, so it becomes minus 0.25. So f dash of minus 0.25 is minus 0.5, and x, so derivative is still negative, so function is still decreasing. Therefore, you further move in the same direction. 0.25 plus, this is the current x, plus the current gradient multiplied by the step size 0.25. Just calculate this value. Uh, so 25 5 is 125.125 from here, and minus, it will be minus 0.125. Okay, and you can keep moving in the same direction. Eventually we'll reach 0. Okay, eventually we'll reach x equal to 0, and we can say this because this is a known function, and we know what is happening basically. But assume that it was an unknown function and you are performing this process on it. You stop it when the gradient of the loss function. Okay, now let's move on. Let's Okay, so let's generalize it to our case of the loss function where we have more than one variables. So this generalizes to that case. Okay, so eventually gradient of f stop when okay, basically you'll have to stop when gradient of f in this case, or that is the derivative of f, is close to 0, approximately equal to 0, close to 0. Okay, derivative value. Okay, derivative is also going on decreasing. If you see, it was -2, -1, minus 0.5. If you further proceed here, that is f of minus 0.125, it will be minus 0.25. So derivative is also decreasing. At some point derivative will be close to 0, close enough to 0, and then we'll uh, stop it. So this process, if I put in form of an algorithm, it is called as the gradient descent algorithm, basically. Gradient descent algorithm. Okay, initialize all variables or parameters or weights. Okay, it is wi. Initialize all of them to some random value. So in this case, we started with x equal to -1. We started at the point x equal to -1. So likewise, start at some point, initialize it, and then calculate the gradient of the function, okay, and update the parameters. So update the parameters or update the variables as, so first for this you'll have to calculate the gradient first. So wi is equal to wi minus, so this is actually, you can actually perform this in a vector form, so I need not even write I in this case. I can directly write it in the vector form. Okay. That is w is equal to w. Now okay, w minus eta multiplied by gradient of loss function of w. Now in this case, okay, if the gradient is positive, function is increasing, it will move, it will reduce w, it will move in the opposite direction. If the gradient is negative, that is function is decreasing, then it will keep moving in the same direction, that is w is equal to w plus. So here this w minus this automatically handles it, multiplied by this learning factor, learning rate, okay, and repeat step 2 until, now there are two cases, until either delta lw, okay, now this is a vector function. Okay, now this is a function of, not a vector function as such, because the output is a number which is the loss, but when you calculate the gradient is the vector. You get this point, w is a vector, okay, consisting of all the weights w1 up to wn. L is a scalar function, and when you apply the gradient to a scalar function, you get a vector, okay, which you all know. So the components of this vector will be delta L by delta W, or del dou L by dou W1 plus dou L by dou W2 plus dou L by dou Wn. And here, okay, so each of these will be multiplied by a unit vector. Okay, so okay, so W1, let's say W1 cap means the unit vector in the direction of W1. Okay, Wn, unit vector in the direction of Wn. This is your gradient of Lw. Okay, so you can write this as, this is uh, gradient of Lw. So the condition is the norm. Okay, you have studied how to calculate the L2 norm of a vector. So you'll have to calculate the L2 norm of the gradient of Lw, and it is less than a certain threshold value. This is a certain threshold value which you have pre-decided according to the problem statement. So let's say when uh, so what is an L2 norm? Basically, it is the distance from the origin. Okay, so when this distance is some value, let's say 0.1 or 0.01, whatever you have decided, when this is less than that threshold value, then we'll stop this repetitions. Or another criteria is, or so repeat until this, or maximum number of iterations, iterations is reached, and you can stop this. Okay, now one last point which is left, and then I'll stop the lecture. One last point is, what about this eta, which is the learning function? Now the learning rate itself has to decrease, has to decrease uh, over the iterations. Only then the algorithm will converge. Okay, so eta of I, I'll write it here itself. Okay, this I can say that it is eta of I, where I is the iteration number, and eta at this particular iteration is defined as C1 upon I raised to A plus C2, and this C1 and C2 are any constants, positive constants. C1 has to be greater than 0. Okay, and it cannot be 0, so C1 has to be greater than 0. C2 can be greater than or equal to 0. Okay, and A is a value always between 0.5 and 2. Okay, A is between 0.5 and 2. Exclusive. Okay, A lies between 0.5 and 2. So this is what is a gradient descent algorithm. Okay, any questions, any doubts? If you have, you can ask. What happens if gradient is 0? Is the function fully optimized then? The gradient is 0. No. Then we have reached, function is not optimized as such. We have reached the extrema. Yes, we have reached the extrema. In a way, yes, you can say the function has reached its optimum value. Okay. Any questions, any doubts? Okay, I'll start the attendance.